Okay. All right, cool. So I'm just catching that. All right. Screen sharing. All right, cool. I think we are good. You ready?
Yep.
Recording beginning. Okay, so for this is our third progress presentation for the semester. Today we will just be going over essentially everything that we have done thus far. So when we first started the semester and we were doing our identification stuff, I don't think we really knew where to begin. Um, there were a lot of possibilities, and we were doing a lot of TLC and things like that. But thankfully, when we finally got our first NMR back, I think that really was a huge plus for us. It really allowed us to kind of get a better identification of what our possible um, unknown dipeptide could be. This is the HNMR. So this was the one that we got back first off, and this was before we had identified our unknown dipeptide. So this was just the first NMR that we got back. You can see multiple peaks, right around 0.75 ppm. There's some at 1. There's a little at about maybe 3.75, a couple at 4, and then we got some at about 7.2 and about 7.9. All of those peaks are labeled accordingly. That HNMR really told us a couple of big things. We saw some peaks in the aromatic region. We saw 2 methyl peaks below 1 ppm, and then we saw the overlapping triplet and multiplet above 1 ppm. And again, those can just kind of be seen here, all of those points. So that was a huge point for us. The next one was the carbon NMR, and the carbon NMR really told us kind of the same thing there. Specifically, 3, 4, and 5 are the carbons that we have marked. 3, 4, and 5 gave us a very, very good indication that we had something aromatic in nature. And that was kind of the first point of which during the identification phase, that we kind of have a way to start narrowing down and really looking at specific amino acids, as opposed to just kind of drawing straws from a hat and testing every amino acid that was in the lab. The other 2 big peaks that we saw were 1 and 2. So 1, 2, 3, 4, and 5 in total really told us a lot and gave us some really and just really good guidance on where to potentially, what aminos specifically to start testing. So as in the previous slides here, we have the 3 peaks in the aromatic region. Those are identified by carbons 3, 4, and 5. And then we also have the 2 carbonyl peaks above 160 ppm, and those are identified by carbons 1 and 2. This was obviously made kind of further down the line, but this is the actual full picture of our dipeptide together. So we have this nitrogen here between carbon 1 and carbon 7, and that is the actual bonding nitrogen. So the nitrogen from the amine group of our leucine here and then connecting to the methyl group of our histidine to make the full dipeptide. So with having those peaks identified, um, especially the aromatic ones, we knew we like I said before, we could break down and kind of focus on specific aminos to be looking at. So based off of those results, we performed more chromatography the following week after getting those back, after getting those NMR back. And what we essentially did is we just started to test um, aminos with aromatic rings in them. So we looked at tryptophan, we looked at phenylalanine, tyrosine, and histidine as well. And upon doing that, we actually saw really good correlations with histidine. And we saw that through the second chromatography that we did, looking at just those 4 specific amino acids, of course, with our unknown dipeptide as well. I'm actually going to jump to this picture first. This one's just kind of the clean, cut and dry version of that. So you can see here's our unknown. Oh, I apologize. This one is, I'll show this one in a minute here. We're actually going to look at this one first. This one, thankfully, it has all of our RF values on it. But the big one that I really want to point out is our unknown, which is labeled here as number 5, and the histidine. And the RF values on our histidine and our unknown are very, very close. So you can see that we measured it at 0.3 centimeters for the histidine, and we measured ours at approximately 0.2. So thankfully, with that, we had an idea. It looked like on the NMR was telling us that we had aromatic molecules. We went and tested, or aromatic aminos, I guess I should say. From there, we went and tested all the aminos that had aromatic rings, and lo and behold, this is what we found. We found that there was that histidine and that unknown. So thankfully, at that point in the lab, in the semester, we were able to at least be very confident in the identification of one of our aminos, and that was histidine. So thankfully, at that point, we knew that we had histidine, and we had something else. We had another unknown amino acid. We had some ideas. We had a couple ideas of what it could be. This chromatography, this one was just kind of the first one that we did. So I believe this is the chromatography paper from day 1 of lab. And this just kind of emphasizes the fact of, like, we were just, pulling straws from a hat. With this one being on the first day, there was no motive, there was no, reason for testing those specific amino acids. Those were just ones that we literally pulled from the bin and did chromatography on them and trying to see what we got. Thankfully, our chromatography on the first day actually came out very, very well. On our unknown here, number 5, just indicating that that's the number, the quantitative number that was given to us at the beginning. So we had the 5th unknown, and all the other groups had 4 and 6 and 1 and 2, etc. But our chromatography actually came out very, very well, and we got we got some really good readings. So
All right, so our next test was determining which amino acid was at the N terminus of the dipeptide and which amino acid was at the C terminus. And just based on our carbon and proton and Mars, we we uh we knew that we had histidine, but we were stuck between leucine and isoleucine as the only other amino acids with the right number of carbons that would match the NMR spectrums because they're both isomers of each other. And so we reacted DNFB solution with our unknown dipeptide and with standard samples of leucine, isoleucine, and histidine, which gave us DMB tagged versions of all our amino acids. And the dipeptide was hydrolyzed in order to give us our tagged N-terminus amino acids and our untagged C-terminus amino acid. And then all of our amino acids were ran on a TLC. And here's the mechanism for the DNFB reaction. It's a nucleophilic aromatic substitution with the nitrogen attacking this carbon, which gives way to a resonance complex, which is stabilized by all the nitro groups. But the fluorine gets eliminated from the DNFB, giving us our DNB tagged dipeptide, and this is the same reaction for the amino acids. And so this is the chromatography we got from all of our tagged amino acids. And you see the isoleucine and leucine had some peaks that traveled relatively further than the unknown number 5 spot, which kind of stayed at the starting point, moving very little. And if you look at the histidine one, the tagged unknown number 5 and the tagged histidine both kind of stuck at the starting position. So this gave us a reason to believe that histidine is the one that is on the N terminus, since the tagged histidine matches the RF value of the tagged known number 5, with the only the N terminus amino acid being tagged.
Okay, so for our titration, after we had done the DNFB, we began to start the titration. Fortunately, the titration for ours, along with many other things, as we went down the road and started to do other things with our dipeptide, really gave us a lot of hassle for sure. So we performed titration on week 3 of the lab. That titration came out absolutely horrible. We could not. We started at a very low pH. I guess I'll just kind of go through the steps here of kind of the nightmare that was titration. it didn't come out correct, and we knew that we would need to redo it. But of course, we wanted to finish the process and see exactly, what we came out with. Um, when when we performed that first titration, biggest problem that we had is we could not get the pH to change on our unknown. Um, it sat at a extremely low pH, which I'll kind of point out those pHs in the next slide a little bit. But it sat at a very, very low pH, and it sat there for a long, long time. It took quite a large amount of sodium hydroxide um, to get it to even do anything, for the titration to even begin, essentially. Once I put a large amount, probably about at least a couple hundreds um, of the using the micro pipettes. Once I got to about an X of roughly 250, so a lot of sodium hydroxide, finally saw some change, but the spike was massive. It was almost like exponential in nature, to the point where it just went almost immediately, boom, it jumped to a pH of 7. Um, it sat there for an extended time, and then it immediately spiked to a pH of roughly 12.5. So the titration did not go very well, unfortunately. We knew that we would need to do it again. So we did it again the next week. We did it on week 4 of the lab, and unfortunately, we did it again, and we saw almost the exact same thing occur. So we were having problems with the pH not only staying low, but we were also having problems with the pH spiking almost too exponentially, to the point where the peaks that we were trying to observe in the titration, we could not see, because the spike was too great. It just kind of wiped out those peaks, and we couldn't see them. So we did it again on week 5. We consulted with Dr. Shoup on it, and she gave us some suggestions on how to kind of do some pH manipulation before starting the titration, before truly starting it, kind of manipulating the pH of our unknown dipeptide, and trying to do some things to get it to have a little bit more of a smooth transition. So we used 6 molar HCl, and we had to drop it. Initially, we dropped the pH of our unknown initially to about a pH of 2. We then actually added distilled water. So it wasn't necessarily a precisely measured amount, but we wanted to add distilled water in there to act as a little bit of a base, to help kind of make it a better starting point for the sodium hydroxide. So that way the sodium hydroxide was not battling this extremely acidic pH that was our solution. So we did that, did things a little bit differently, and sure enough, we came out with excellent results. These results can be seen here. So this is just our pH versus NaOH, the sodium hydroxide measured in microliters. So you can see here, we went our our domain, I should say, spans between 0 and 160. Our range spans between the standard 0 and 14. So this right here is the point at where we started with our titration. So we were give or take, 1.7 ish, right around that area. Started to add the sodium hydroxide, and then we actually started to see this nice flow, and this is really what we were after. as opposed to the previous 2 weeks, what happened is we just sat at this constant pH for a ridiculously large or a long time. We our NaOH, I believe, was in the I think it was right around the 200s before I even saw anything occur. And when it did, it immediately, instead of having this nice flow and identifying the peaks, it literally just shot up exponentially. So it went more of just a straight line, and then it leveled out again. So we saw much better results. When we initially did this, we couldn't quite tell, but it looked like there was a peak right around 75 microliters relative to the x-axis. We knew for sure, we were confident in peak B, we were confident in peak C as well, but we weren't quite sure if there was one popping up there, what is now marked as peak A. So we just used Microsoft Excel, these calculations, the error bars, everything like that, that was not calculated by us. That was simply calculated using Microsoft Excel. So we actually just took the derivative of our data, and sure enough, we found boom, boom, boom. We found 3 peaks. So this is peak A, this is peak B, and this is peak C. And this just kind of helped validate the fact that we did, in fact, our hunch was correct in that first slide, to where we did in fact have 3 peaks. And those can be simply just shown here. I just marked those in red. That way they're, they're clear. So we got the pH of 2.86 at 75 microliters. And there is the dy dx. Same thing here, 5.98, 90 microliters of sodium hydroxide, and a pH of 10.6 at 115 microliters of sodium hydroxide.
So the cozy NMR showed us more kind of it mainly identified which of the methylene peaks around 4 belong to which methine peaks belong to which amino acid. So we got HE and HD, and we figured out HE is the more downfield peak, because HE interacts with HG, as seen circled in blue, while HD interacts with HF, as seen in yellow. And here's a table of proton interactions. And now to the HMBC NMR. This helped us figure out which of the carbonyl carbon peaks belong to which amino acid, because the carbonyl carbon on the C terminus only interacts with the methine protons on the C terminus, but the carbonyl carbon on the N terminus interacts with both methine protons on the C and N terminus. So you see here that carbon 2 interacts with HE, while carbon 1 interacts with HE and HD. So that is so carbon 2 belongs to the C terminus, which is leucine, while carbon 1 belongs to histidine. And 7 and 6 shows us which of the methine carbons interacts with which of the methylene protons on the side chains, since both side chains have methylene groups. And so it's hard to see in this table right here. So if we scroll to the correlation table, we see that carbon 7 interacts with G and H. So G right here and H right here. So that means carbon 7 belongs to the leucine amino acid, while carbon 6 interacts with F, which belongs to the methylene group on the histidine side chain. So carbon 6 or carbon 7 is more upfield than carbon 6. And for carbons 9 and 8, those are the methylene carbons on both side chains. We were able to figure out that carbon 9 interacts with both carbon 9 interacts with H, protons H, I, and J, which are the part of the isopropyl group on the leucine side chain, while carbon 8 interacts with D, which is the methine protons on the histidine side chain. And so using the HMBC NMR, we were able to figure out the carbon peak assignments. And that's the correlation table.
Okay. After getting all that data, we ran optical activity. Optical activity, unfortunately, did not really tell us anything. We did it just to simply do it. You know, we didn't know at that point what it would bring us. So we simply just did it. Here's all of our values, our density, our path length, etc. After performing it, and I put the equation right here so you can see it as well. But we measured the specific rotation alpha, and that is simply just the observed rotation divided by the density multiplied by the path length. When we did that, we got negative 117.9487. Now, unfortunately, this number did not really do anything for us because when we looked at the standard numbers, so just the textbook values of what the specific rotation of each of our individual aminos were, we did not really see anything, unfortunately, that was very useful. So overall, optical activity, we did it, but it didn't really bring anything to the table for us. And just kind of overall, didn't really do much. So after all the identification steps had been done, we started synthesis. At this point, we were confident that our unknown dipeptide was leucine and histidine. So we started synthesis, started with the standard 1-to-1 ratio identified here. So 1-to-1 ratio of hexanes and ethyl acetate. We ran into a lot of problems with synthesis as well. I think we ended up doing synthesis for, I want to say 4 weeks, so almost a month of just doing synthesis because unfortunately we were getting stubborn results, very stubborn aminos. So we started with the 1-to-1 and we saw no success. So after consulting with Dr. Shoup, we changed the concentration of our ethyl acetate. So we went to a 1 to 2. We also went to a 1 to 3. We were starting to see change. We were starting to see better separation of our unknown, but it still wasn't great. And we noticed that the separation was getting better as our ratio of specifically the ethyl acetate increased. So we just decided, what the heck, let's give it a try. So we tried a 0 to 1, so no hexanes whatsoever. It was just pure ethyl acetate. And we saw success. We saw separation of the dipeptide that was much better than any of these other ratios were. This slide shows that. So this shows the 1.1. As you can see here, like no separation. 1 to 2 got better. 1 to 3 got a little better, but our goal was really to get this more upfield. And we saw that, as we were increasing the concentration of the ethyl acetate, it was in fact moving more upfield. So this is our pure ethyl acetate. And we got, as you can see, much better separation. Now the problem we were running into was the massive amount of streaking. In order to try to solve that issue, we put 3 drops of methylamine to the synthesized sample, but unfortunately we did not really see much success. So again, here's the pure ethyl acetate sample, and here is the ethyl acetate with the methylamine. And unfortunately, you really probably couldn't, generally tell much of a difference between the two. So we tried it, but we could not get rid of the massive streaking like at all. It was unfortunately something that we were kind of just having to work with and move on. So here is all of the TLC that we did with this image. A little harder to see, but at the top here we have the time, the times marked of when we were doing it. These are just kind of an accumulation of all of the synthesis that we performed.
All right, so we obtained NMR samples at different parts of the synthesis. So this is right after we did the acid base wash workups. And not much to say about here. Definitely huge peaks, but I feel like most likely those are solvent peaks. There's some peaks in the aromatic region, but let's see. And this is after we started a column chromatography, and these were the fractions number 7 through 12, and these were with 1-to-1 hexane ethyl acetate. And it seems like it's mostly solvent peaks. And let's see, fractions 13 through 39 showed see even larger peaks, or actually see what looks to be mostly solvent again. The fractions 40 to 45, on the other hand, had some different peaks showing up, such as see, from 8 to 7 we started seeing the aromatic peaks again, as seen in the earlier post workup, and those would correspond to the FMOC protecting group on the N-terminus of the dipeptide, and the trityl protecting groups on the histidine side chain, since those are in the aromatic region. And we see a couple more peaks a little bit above 6, which could be possibly possibly amide bonds, or could be, but starting to see around 2 and below, we see giant alkyl peaks, which could possibly be the methyl groups on the leucine side chain. So there's definitely some reason to show that our synthesis product is in fractions 40 to 45. And let's see, after our those fractions, we just pulled everything together. And these are just more peaks, could be solvent.
All right, and then to wrap up presentation here, we just recently started the purification after doing all the synthesis and just kind of calling it. We combined our 40 and above. So we did 40 to 45 and then 46 plus, combined those into one solution and ran that for our column. So we did our column and unfortunately ran into many more struggles. So we performed the column, did 10 plus fractions, no visible TLC whatsoever, like nothing. You would never even know that we used the glass pipettes to put sample on the TLC. The TLCs were blank. 20 plus fractions, same situation, no TLC whatsoever. 30 plus fractions, still no visible TLC whatsoever. And then right around fraction, at fraction 42 actually, we did see something starting to show up. Unfortunately, it's not super clear. You can kind of see it here and here, but I put these lines just to indicate where the top of the peak was. But the peaks, unfortunately, were not clear enough for us to actually draw like a good kind of outline of the TLC. It just wasn't strong enough. But we were at least seeing something. And thankfully, one thing that I thought was a huge positive is that as we went higher here, 42 and then fraction 43 and 44 and 45, those peaks were actually getting higher, which was a good thing. That indicated to us that that we potentially, that is where our sample was. It just took a long time for us to actually get it through our column. So we combined our fractional groups in groups of 10 and rotovapped it and sent it to NMR. With the results of the NMR based off of our previous slides here with our 40 to 45 and 46 plus, we combined, we decided that those were the best samples to combine. So we combined 40 through 46 plus. We performed a second column, kind of the same situation. We got to 30 plus fractions with no visible TLC. That was absolutely horrible because we had something there and then it was gone. So I cried inside a little bit. And then we collected 36 plus fraction remaining in the column and just said, you know, there's something here. Let's shoot the NMR. NMR will probably be able to see what the TLC cannot. And sure enough, here we are. We just got this back last night. So we haven't had, unfortunately, a great amount of time to really look at this, but we figured we would, of course, put it into the presentation. So this is our 37 plus, very zoomed out. We ran this just so you could identify the peaks here, right around 4 and 2, and then 1.6, give or take. And this is the zoomed in. So we got a lot of activity going here. We've definitely got some peaks for the final presentation. We should have some better analysis done on this at the current moment. We just got it back less than 24 hours ago. So we were not able to run a ton of analysis on this, but we do have it. And for the final presentation, we should hopefully have something better. So with that, I think we are finished. Thank you so much. And we will see you for the final presentation.